welcome back. Now we are doing section 13.3 in Business Math 1105. In this section, we will be studying concavity. And also we will be discussing points of inflection. To start with, we need to know how a concave upwards curve looks like and how a concave downward curve looks like. On the xy plane, I put in front of you two curves. We can see that one of them is concave up and the other is concave down. Concave up, whenever you draw a line joining any 2 points, you will find that the line is falling above the curve. Here we call it concave upwards. On the other side, concave downwards, if we try to draw any line joining any 2 points, you will find that the line is falling below the curve. We call it concave downwards. In this course, we have a condition for concave upwards where it is put on the second derivative. Whenever you have a second derivative of the function greater than 0 on a certain interval, then on this interval the function f is concave upwards. But if you find the second derivative of a function on a certain interval less than 0, then on this interval the function will be concave downwards. Okay? And then we see a value of x. Let's say x equals x naught. If this x naught is in the domain of the original function, and you find that the curve to the left and to the right flips concavity, concave upwards to the left and then concave downwards, or concave downwards to the left and then becomes concave upward, in this case, where the x naught is in the domain of the original function, you can have an x naught, y naught point, where you call it point of inflection. So let's take an example to illustrate all this. F of x equals 6x power 4 minus 8x cubed plus 1. We are asked to test concavity and points of inflection. First of all, let's agree that we have a polynomial function, so the domain for this function is all real numbers. Okay? Second, we need to find the second derivative so that we compare it to 0 and find the intervals on which the second derivative is positive or negative to see the concavity. So we have f prime equals 6 times 4, 24, x cubed minus 24x squared. This is the first derivative. Now the second derivative, f double prime equals 72x squared minus 48x. Now we will simplify this. F double prime equals 24x common factor, and inside now I will have 3x minus 2. What are the values of x for which f double prime of x equals 0? These are two values, either x equals 0 or x equals 2 over 3 from the second bracket. Now we take these values and immediately we go to the real line and put them on the real line. This is 0 and this is 2 over 3, where these split the real lines to 3, interval 1, interval 2, interval 3. Now we have our second derivative as a product of two things, which will change its sign. The x and the bracket, the x and the bracket, the x and the bracket. And on each interval, I will take a test point to see the sign of the second derivative. If I take anything less than 0, here I will have a negative. Now, let's say we take minus 1. 3 times minus 1 is minus 3. Minus 2, it is minus 5. I don't care for the value, I care for the sign. If somebody else takes minus 4, again, minus 4 times 3 is minus. Again, everything is minus. So this is positive, telling us that on this interval, the second derivative is always greater than 0. Whenever we have a second derivative greater than 0, then this tells us that the function is concave up. Now, between 0 and 2 over 3, I will choose the 1 over 3. Again, the 1 over 3, if I put it here, it is positive. 1 over 3 times 3 is 1, minus 2, it is negative. So the whole thing is negative, telling us that the second derivative on this interval is less than 0. And whenever we have a second derivative less than 0, then we can say that this function, the function on this part is concave downwards. Again, greater than 2 over 3, I can take 5, I can take 10, I can take 200. Any value you put here is positive. 10 times 3, 5 times 3, 500 times 3 times minus 2, also it is positive. So the whole thing here is positive. That's to say that the second derivative is positive everywhere on this interval. So we have the function to be concave upwards. Now, let's look at these values. Do they belong to the domain of the function? Yes, they belong to the domain of the original function. So we can call them points 0 and f of 0, 2 over 3 and f of 2 over 3. These 2 points are points of inflection. You go ahead and substitute for 2 over 3 here and substitute for 0 here. I think here is 0 and 1, while this 2 over 3 and something, it's minus 5 over 27 from the book immediately. So now we found the intervals on which the function is concave upwards and the interval on which the function is concave downward. We found also the points of inflection. You can rewrite what you got here as from minus infinity to 0 to union from 2 over 3 to infinity, f of x is concave up. While on the interval from 0 to 2 over 3, f of x is concave downwards. Next, I'll be doing an example to sketch a graph of a function using the information of concavity, our knowledge of concavity. Okay, now we should take an example. Y equals 2x cubed minus 9x squared plus 12x. We are asked to sketch the graph of this function. As we know, to sketch the first step, we need to find the x and the y intercepts. So let me rewrite this as y equals, I'll take an x common factor, and here I will have 2x squared minus 9x plus 12. When you say y intercept, you put x equals 0, you will get y equal 0. Now, when you say x-intercept, you put y equals 0 and find the values of x. This is equal to x times something written in the parentheses, 2x squared minus 9x plus 12. Again, we will have two options, either x equals 0 or the bracket 2x squared minus 9x plus 12 equals 0. If we look at this and we recall that in the pre-calculus course, we used to find the discriminant, which is b squared minus 4ac. Now, b squared is 9 squared minus 4. A is 2, c is 12. So this is 81 minus 8 times 12, which is 96. This is less than 0. So this can never be equal to 0. So the x-intercept will be at y equals 0, x equals 0. So we have the x-intercept to be 0 and 0 only. So this is our x-intercept and y-intercept. Next, we should find the first derivative, because the first derivative helps us to find the intervals on which the function is increasing or decreasing. Also, it helps us to find the critical values and the relative extrema. Okay, so we take y prime equals 6x, we are differentiating here, squared minus 18x plus 12. What are the values of x which will make y prime equal 0? I take 6 common factor. I have x squared minus 3x plus 2 equals 0. I can factor this x minus 2, x minus 1 equals 0. Here I have two possibilities, either x equals 2 or x equals 1. And these are the critical values that, because they belong to the domain of the function, as the function is a polynomial, so its domain is all real numbers. Good. Now, what should I do with these values? I take them and I put them on the real line, and I study to the left and to the right of each of these values. I have 1 and I have 2. So I have 2 brackets. The first derivative is 6 times 2 brackets, and 6 times 2 brackets. Also 6 times 2 brackets. I take something less than 1. Should I take the 0? What do you think? If we take the 0, it's interesting. So 0 here, minus, minus. So the whole thing is positive. So it tells us that f prime is greater than 0. So the function is increasing. I take between 1 and 2, 1.5. 1.5 minus 2 is minus. 1.5 minus 1 is positive. So the whole thing is minus. So f prime is less than 0. So the function is decreasing. And now we go. Take 3 bigger than 2, or take 4. 3 take away 2 is positive. 3 take away 1 is positive. So the whole thing is positive. So f prime is greater than 0 here. So the function is increasing. Next, we try to rewrite this again. I have an increasing to the right of 1. The function is increasing and then decreasing. Then at the point 1 and f of 1, we have relative maximum. And then to the left of 2 and to the right of 2, it's decreasing and then decreasing. So at the point 2 and f of 2, we have a relative minimum. Good. So here, this point is 1. I take the 1 and I substitute here. So we get 1 and 5 as the value for F1. And here we get 2 and 4. Okay, so this is the maximum and the minimum, the points corresponding to the maximum and minimum. What should we do next? We should study concavity. So here in the first part, we were talking about intercepts. In the second part, we are talking about the places where the function is increasing, decreasing, and critical values which will lead us to find the relative maximum and minimum. Now we should talk about concavity. We go to the first derivative in front of us here, and then we differentiate again. For concavity, we need to find y double prime. Y double prime, again, you differentiate. 6 times 2 is 12x. So here I have 12x minus 18. And we ask the same question. What are the values of x for which y double prime equals 0? Simple enough. 12x equals 18. X equals 18 over 12. This divided by 6, it is 3 over 2. So I have a point that is called x equal to 3 over 2. I take it to the real line and I study to the right and to the left of 3 over 2 the sign of y double prime. Our y double prime, if we can write it as 6 into 2 minus 2x minus 3, this will make our life very simple, and then we try to find to the left and to the right the sign of the second derivative. To the left of 3 over 2, the easiest thing is that you take a 0. So if you put 0 less than 3 over 2, y double prime here will be less than 0, so this is concave down. To the right of 3 over 2, take anything bigger than 3 over 2. You can take 5, you can take 10, whatever you put, then you should get y double prime is greater than 0, tells us that this is concave upwards. Notice that the domain of the original function is all real numbers. So, and this point, at this value of x, we can see that the curve is flipping concavity from concave down to concave up. So I can find a point 3 over 2 and f of 3 over 2 to be called point of inflection. Next, we take everything and we go to the real line. We take everything and we try to sketch it on the real line. I will put this as the x-axis and the y-axis, and I'll try to sketch in this small place. As we've seen earlier, that we put first the points which are intercepts. The intercepts are 0 and 0. Next step, we put at the point 1, what do we have? And at the point 2, what do we have? At 1, we have a relative maximum, which is 1 and 5. This is 1, 2, 3, 4, and 5. At 1 and 5, we have a point here. This point is talking about relative maximum. So can I put a little cap that tells us that there is a maximum here? Yes. And now, what's next? 2 and 4? Okay, we put 2 and 4 on the curve. Again, 2 and 4 is a relative minimum. So can I put a little cap that tells me minimum? Yes. Okay. Now, if we look at this given function, the original function here, what is the leading coefficient? It is x cubed. Is it having what is the leading term? Sorry, it's x cubed. The leading coefficient is positive. I'm expecting an x cubed from pre-calculus to have the terminal ends in different directions. So I'm expecting a terminal end here, and I'm expecting a terminal end on this side. Now let's take the gray pen and try to connect everything. The terminal end tells us to the left of 0. I should go up because the function is increasing to the left of 0. I go up, increase, keep increasing until you reach 1. Okay, so we keep going until we reach 1. And then after 1, between 1 and 2, the function will decrease and it will flip concavity at some point here, which is 1.5. At this point, 1.5, the function flips concavity here, 3/2. Yes, can we see that it is flipping concavity? Yes, it was concave down all the way until it came here, and then it will start flipping concavity, and we reach over there. So this is the sketch of the graph. Thank you very much.